Blue whales are the largest and loudest animal. They have very low-pitched voices. Based on this, circle the best wave. So recall, we want a amplitude that, remember, amplitude is related to energy or loudness and the height of the wave, whereas frequency is the total number of waves per cycle, and that is related to the pitch or what their voice actually sounds like. So let's go ahead and take a look here. First off, go ahead and point for me on the board. Which of these have the largest amplitudes? All right, which ones have the largest heights? Because again, we said we have the loudest, they're the loudest animal. All right, so we need ones that have big heights, big heights. Tell me which ones have big heights. Yeah, so this one, awesome. Let's get some more answers up there, get some more arrows. Which of these two have the biggest heights? Which of these two have the biggest heights? Thank you, red. Thank you, purple. Thank you, pink. Yeah, perfect. So we're going to get rid of these ones. These ones don't work. Their amplitudes are much smaller. Those are going to be quieter animals. Now, then we also said that we have low-pitched voices. So low-pitched voices means that we have lower frequency or less waves. So go ahead and tell me which of these two has less waves compared to the other one. Find the one that has less waves. Point to the one that has less waves. Thank you, purple. Thank you, red. Thank you, green. Let's get some more answers. Pink, find the one that has less waves. Less waves. Again, they have the same height or amplitude. Yeah, perfect. So taking a look here, this one right here has both the large amplitude and the low frequency, right? We can see it's really big, which means it'll be loud, but there's only like one and a half, not even, there's like one wave and a little bit here. So this is a really low frequency, low amount of hertz, and that would correspond to a low pitched voice. Go ahead and give me smiley faces, everyone, if that makes sense. Let's go ahead and get smiley faces. Angelina, Amari, Cody. Get those smileys in the chat. Thank you, Angelina. Thank you, Mallory, Shayna, Amari. Excellent. Give me smiley faces if you understand. Matthew, Callie. Thank you, Cody. Timothy, Jalen. Go ahead, give me smileys in the chat if you understand. Seraphim, you too. Great. So just some quick facts about blue whales. Blue whales are the largest animal ever recorded to live on Earth. They can measure up to 100 feet long, which is 3 buses. So not just one school bus, but 3 school buses. And they can weigh 441,000 pounds. That's a big that's a big whale. Their tongue weighs as much as a single elephant. All right, so their tongue is so heavy it weighs as much as an elephant. They are the loudest animals on the planet. Again, that's why we had a really large amplitude because they're really loud. But again, they do have low voices, so low pitches, which means only a few waves per second, a few hertz, right? So blue whale frequency is 10 to 40 hertz, and humans can't even hear below 20 hertz. So a lot of the sounds whales make, we can't actually hear. We can only observe them through using like technology, which is pretty crazy to think about. And they, even though they're really big, they can actually live for a pretty long time. Usually bigger animals don't live as long, but here they can actually live 80 to 90 years on average. I saw an article recently. I didn't do a lot of research on it or really read the article, but I did see a title of an article that said that it might have something to do with the fact that their own cancer cells actually then get cancer themselves, and so that cancer wipes out the other cancer cells, which is why they can live so long, even though they have a lot of mutations that can happen in their bodies. So again, pretty crazy to think about. All right, let's go ahead and go over some announcements here.
All right, guys. As always, please don't share any personal information during class. Your participation is still required, and these sessions are being recorded for learning purposes. All right, so we are on Monday, so fresh start of a new week, marching right through Unit 4. Let's see what we're doing. All right, so we're going to now calculate the speed of sound. All right, and we're going to calculate the speed of a wave using wavelength and period, and then we're going to calculate the speed of a wave using wavelength and frequency. Okay, let's go ahead. See how many of us have our notes out. All right, most of us, that's good to see. Only a couple of you. I'm looking for Callie, Anissa.
Awesome. All right, everyone. So let's go ahead and talk a little bit about the speed of sound. So this is actually very recent research. On Friday, October 9th, physicists proposed that the fastest sound can move is about 36,000 meters per second, which is pretty fast. Not as fast as like light, right? Light is extremely fast, but sound can move pretty fast theoretically. Now, the medium, meaning the substance in which they base these calculations, is not a substance that we have yet been really able to synthesize, right? So this is hydrogen, but if you make hydrogen solid, it actually can turn into a metallic form. So they said that the fastest sound can move would theoretically be in solid metallic hydrogen, which normally hydrogen is a gas in our everyday life. So take a look at this data here, and we're going to try to figure out, why does this hypothesis make sense? So taking a look up here, tell me in the chat, when is sound fastest? Is it fastest in gases, liquids, or solids? Go ahead and tell me in the chat. Is it fastest in gases, liquids, or solids based on our first chart up here? Thank you, Shayna. Thank you, Angelina. Yeah, definitely, Joseph. Definitely, Mallory. It's fastest in solids. Take a look at like steel and glass. It's moving at 5,000, almost 6,000 meters per second. So yeah, so first off, that makes sense that, right, we want something that is solid. Now, the reason we want something solid, we saw that domino example of like the closer dominoes are, the faster sound can move through them, or the faster you can send on a message. That's because close particles can hit each other faster, right? So if you imagine like a game of telephone, the more people that you can pass that message onto, the faster it goes, right? So solids, particles are closer. Awesome. Now, additionally, let's go ahead and take a look at just talking about the actual type of chemical. So taking a look here, which of these chemicals or gases does sound move the fastest? Go ahead and tell me in the chat. And in this chart, where is sound moving the fastest? Yeah, exactly. If you take a look at our data here, it's moving the fastest in hydrogen, right? 1,270 meters per second, right? So here we go. We could see that we also have this idea of hydrogen here. Okay, now the reason that sound moves faster with hydrogen is because hydrogen is actually the smallest. Right? It's the smallest atom on the periodic table, which we don't really go into why the size of the atom really matters, but just know that the smaller an atom is, the faster sound can move through it generally. So bigger things like krypton, right, is 221 meters per second. Krypton is much larger, and so krypton doesn't pass on that message quite as quickly. Smiley faces emojis in the chat if that makes sense. Okay, so we know that small particles pass on the message faster, and solids, where the particles are closer, pass on the message faster. So putting it together, that means that if we can make both a solid and hydrogen at the same time, solid hydrogen, then theoretically that would be the fastest medium in which sound could possibly move. All right, so that's where physicists came up with this, and again, their calculation came out to 36,000 meters per second, which is really, really fast for sound. Think about when you and I talk, sound only moves at 331 meters per second in our everyday lives, or 343 actually, because we're at room temperature. So it actually moves pretty slow for us in everyday lives. So just an interesting review on, right, how sound can change in different mediums, and just some recent research, right? So moves faster in solids and in smaller gases. So put it together, solid hydrogen is going to be the solid and the smallest. Cool. All right, so let's go ahead and talk about how to calculate speed. So the speed of sound is the rate at which we pass the disturbance, the actual sound, and how fast it gets passed from particle to particle in a medium. Again, sound needs mediums. Sound can't travel in a vacuum, can't travel in empty space. It needs something to travel in. Now, we have already learned an equation for speed, which is the speed of an object is distance divided by time, just like how when you are moving at 30 miles per hour, that's 30 miles divided by hours. All right, go ahead, give me a green check, orange X if you remember that from our very first unit. Distance divided by time is our equation for normal speed. Right, 30 miles per hour is the same as 30 miles divided by hours. Great. Now we can go ahead and take the same equation and just kind of convert it to vocab for waves. Okay, so the speed of a wave, okay, so v meaning velocity or speed, is going to this time be the wavelength, because that's the distance of a wave. So wavelength wavelength, or the distance of a single wave, okay, divided by the time, but in this case, time is specific for a single wave. So that would be the period. So the period would be the time of a single wave. Okay, so it's still distance divided by time. It's just specific to the distance and time of waves. Go ahead and give me a smiley, medium, or sad face if that's beginning to make sense. Again, it's the same equation, just in terms of waves. We're just kind of changing the vocab. Great. Okay, perfect. Just so you know, this symbol right here, this upside down looking Y, is actually the Greek letter lambda. So you'll hear me say lambda a lot. Lambda, L-A-M-B, again, is just a Greek letter that stands for wavelength. Okay, kind of looks like a wave. All right, so let's go ahead and try this out. A single sound wave travels 0.926 meters in 0.0027 seconds. What is its speed? So you can see a sound wave here, and we're going to go ahead and figure out what we need to plug in here. So go ahead and tell me in the chat, 0.926 meters. Meters is my unit for what with waves? Take a look at our chart here. Meters is our unit for what? Go ahead and tell me in the chat. Meters is my unit for what? Thank you, Angelina. Let's get some more answers. Thank you, Amari. Again, we're just practicing, so we're starting out. Meters is my unit for what? Thank you, Joseph. Thank you, Amari. Make sure you're not just copying what other people say. Make sure you're actually typing it out yourself. Benjamin, Kai, Anissa. All right, we all have the same spelling mistake with wavelength. So again, make sure that you're actually doing it yourself, because otherwise it seems like you're just copy pasting what the person said up of you. All right. I'm already caught onto that. All right, so here we go. Yeah, this is going to be our wavelength, right? So I'm going to go ahead and label that as my lambda. All right, and 0.002 seconds is normally time, but again, in terms of waves, we call this what? All right, seconds now is the unit for what? Oh, you just typed it, but you typed it the way that they wrote it. Gotcha. All right. No worries. Tell me in the chat. Seconds is our unit now, not for time, but for what? Again, it's time for a wave, which is called the what? Yeah, it's actually called the period, right? So this is abbreviated with a capital T. Capital T. Okay, so let's go ahead and plug that in, right? So on top, I have my wavelength, all right? So I'm going to plug that in. 0.926 meters, just like a distance normally gets plugged into an equation, into a speed equation. And on the bottom, I've got my period, capital T, which is going to be 0.0027 seconds, just like seconds time usually gets put into a velocity equation. Now let's just go ahead and solve it. Grab a calculator on your phone, on your computer, or Google the word calculator and a calculator will pop up. What do we get here? So 0.926 divided by 0.0027. Excellent, Angelina. Keep in mind the number on the bottom is really, really tiny, so you actually should end up with a really big number. Because if you divide something by a really small amount, you actually end up with a big thing overall. Go ahead and tell me in the chat. Thank you, Cody. Let's get a few more answers in the chat, please. Callie, Jayland, Kamal, Timothy. You will need to be able to do a few of these calculations on your own today, so make sure you're practicing. That's the whole reason we do this. No worries, Jaime. Thanks for getting here. You're good. All right, so 0.926 divided by 0.0027, we should end up with a speed of 342.96 meters per second, which you will notice if you look back at our old chart is actually just the speed of sound in room temperature air. All right, so that was intentional here. So here we go. How do we feel about this? Go ahead and give me green checks, orange X's if you're starting to feel comfortable with this. Again, we will have lots of practice today, but it's just like our normal speed equations. Seriously, it's very, very similar. Cool beans. All right, let's do this. Here we go. This is our answer for number 2. Fill in the blank with 342.96 for the first box. The second box, units for speed, is meters per second, just like with objects. All right, so first box, 342.96. Don't forget those decimals. Second box, meters/seconds, m/s. Go ahead and take 20 seconds to fill that in and raise your hands. All right, so here's the deal. We just learned how to calculate speed of a wavelength, much like we calculate speed of an object, right? There was a length, right, a distance, wavelength, divided by a time, right? Our period. Period is the time for a wave. However, you can actually also calculate the speed of waves with a frequency as well. Now remember that we learned that frequency is just the inverse or opposite of period. So we learned that frequency is 1 divided by period from one of our previous classes. Smiley faces, emojis in the chat if you remember that. Frequency and period are just opposites. Frequency is the number of waves in 1 second. Period is the time for one wave. All right, so they're just opposites. So taking a look at our equation again, the one that we just learned, speed of a wave equals wavelength divided by time, we can actually change this to instead have frequency. All right, the way that we can do this is by separating this out. So if I take lambda by itself on top, that's the same as saying lambda over 1. And if I take period by itself on the bottom, that's the same as saying 1 over period. And I can just multiply those together, okay? So what you can see here is I have lambda over 1 times 1 over period. That's the same thing as saying lambda over period. Okay, we don't need to know that much about this. This is just to prove to us that this can change into frequency. So the way that we then do this is then 1 over period, we just saw up here, is the same thing as frequency, right? So we saw that right here. 1 over period is the same thing as frequency. So instead, I can just put F right here for frequency. So now I have a new equation where speed equals lambda times frequency. Okay, so again, what you'll just notice here is that it's the opposite equation, right? Previously, we had lambda divided by period. Now we have lambda times frequency. Go ahead and give me a green check, orange X if that's beginning to make sense. So I can still solve for speed with frequency, but just by doing the opposite function. Instead of dividing by period, we're going to multiply by frequency. We're just going to do the opposites because frequency and period are opposites. Let's go ahead and try this out. So I have a 400 hertz sound wave that has a wavelength of 0.9 meters, and I want to know what is its speed. Tell me in the chat, what does hertz tell us? Hertz is the unit for what? Oh, I don't have it up here. I apologize. Hertz is the unit for what? We should know this though. Excellent. I see Shayna in the chat. I see Angelina. Yeah, beautiful. Hertz is the unit for frequency. Perfect. And meters right here, we just said was the units for what? In terms of waves, it's the units for what? Not distance, but in terms of waves, the distance of a wave is called the what? Thank you, Amari. Again, meters in terms of waves is called the what? Yeah, it's called the wavelength. So again, I'll label this one as lambda. All right, so plugging this in for lambda goes 0.9 meters. Okay. And in for frequency should go 400. And tell me in the chat, what do you get? What is 0.9 times 400? Again, we're calculating a speed. The units for speed should end up being meters per second, just like normal. And Mallory and Jalen first up. Great job. I see Angelina and Cody. Beautiful. Again, you're going to get a couple more practice problems, and then the last ones you have to do on your own. So make sure you're practicing with us so you feel comfortable with that last one. Yeah, you should be getting 360 meters per second, which right here is going to be our answer for number 3. So in the first box, remember, put the number 360, and in the second box, please put m/s, which represents meters per second. You have 20 seconds to answer that, and raise your hands.
The question on the left. All right, waves in a lake are 8 meters apart and pass a raft every 3.2 seconds. What is the speed of the waves? All right, so we have lambda over t, right? So we're going to have a length of wave for every unit of time. So, right, we have our length, right, up here for every unit of time of being 3.2 seconds, and we're going to divide the two. So 8 goes up here. If you can quickly just calculate that so we can all confirm that we get the same answer. What is 8 divided by 3.2? It travels 2.5 meters. So 2.5 meters, that's the speed of the waves in the lake. All right, and now the question on the right. A 110 hertz wave along a guitar string has a wavelength of 0.65 meters. What is the speed of the wave? Right? So now we're dealing with lambda and f. So we have wavelength and frequency, right? So our frequency is 110 hertz and our wavelength is 0.65 meters. We're going to multiply the two together. So this is going to be 110 over, or I'm sorry, scratch that, wrong place. This is going to be 0.65 for our frequency.
Sorry, there's some confusion in the chat. So again, 110 hertz is the units for frequency. So again, I know it's not in the chart right here, but 110 hertz, make sure that you know that when you annotate this, this is frequency. All right, smiley faces, everyone, if that makes sense.
Yeah, sorry about the, we're dealing with just straight up time. That is our period. Okay, everyone, that is our period. Okay, the reverse of that, right, is hertz. So inverse, that's why we're multiplying it instead of dividing it, because it's the inverse of our period, right? All right, I'm sorry, 110, my mistake. I'm getting sloppy. All right, 110 times 0.65. You know, what decimal place do you round to? Because this should be a terminating decimal. All right, awesome, yeah. Let's get a little more in there. Remember your units. Yeah, exactly. 0.5 meters per second. That's the speed of the wave on a guitar string. All right, very good, everyone. This is going to be number 4 and number 5. So please go ahead and raise your hands when you are done with these and ready to move on.
All right, so this last one we need to go ahead and be able to complete on our own, but I'm going to go ahead and help you set it up and annotate it. So taking a look here, it says a wave in a rope is 5 meters and takes 2.7 seconds to occur. What is the speed of the wave? So let's go ahead and take a look here. 5 meters, meters in terms of waves is the what? Again, it's normally a distance, but in terms of waves, this is called the what instead. Tell me in the chat. Thank you. I see Angelina working. What does meters stand for? Thank you, Shayna. Let's get some more answers. Amari, thank you. Let's get Jaime, Kalina in the chat. Kai, Joseph, Benjamin, Noah, Matthew, Jalen. Go ahead and tell me in the chat. Meters is our unit for what when we're talking about waves? Thank you, Cody. Again, waiting on some more answers. Jonathan, Kalina. Kai. Awesome. Thank you, Joseph. Waiting on Benjamin. Noah. Hello. Yeah, awesome. So meters right here is going to be our units for wavelength. Perfect. And now taking a look here, 2.7 seconds is normally time, but for waves, we instead use what? Instead of time, this stands for what? Seconds is our what? Awesome. I see Cody in the chat. Oh, Cody, so time for a wave is called the what, though? Awesome. I see Angelina. Again, let's get some more answers. I haven't seen answers in a while from Jonathan. Kalina. Kai. Benjamin and Noah. Thank you, Noah. Thank you. Benjamin. Awesome. Thank you, Seraphim. Yeah, so right here we said that time for a wave is actually called the period. Thank you, Benjamin, for participating. Yeah, so now we know our wavelength, we know our time, we should be able to plug those in. Remember, you should divide the top by the bottom. So top goes first into your calculator. And then units here should still be meters per second. For this, you do need 2 decimal places. So it should be point blank. All right, so you should have a number, point blank. For your first box, and your second box should still be meters per second. Go ahead and raise your hands for number 6 if you want to check your answers. We're in the Q&A chat. Take advantage of that. You have 30 seconds to work on number 6. All right, so let's go ahead and take a look at our last question here. So a slinky is 0.7 meters long. You create a wave in the slinky with a frequency of 3.4 hertz. What is the speed of the wave? So let's take a look here. Meters, again, is our units for what? Again, the distance of a wave is called the what? Distance of a wave is called the what? Yeah, exactly. I see Angelina, I see Kalina in the chat. This is going to be our wavelength. Good. And right here, hertz is our what? If you read the question, it actually tells you. Hertz is our unit for what? Again, this was something that we were a little bit weak on before, so let's make sure that we feel comfortable with this now. Hertz is our unit for what? Thank you, Angelina. Thank you, Amari. Thank you, Lena. Tell me in the chat, Jonathan, Joseph, Benjamin, Noah, Shayna, Matthew, Seraphim, Timothy, Kamal, Jayland, Angelina. Hertz is our unit for what? Thank you, Jonathan. Carlos, tell me in the chat. Thank you, Matthew. Yeah, exactly. So hertz, it literally says it right there. That's our frequency. All right. So you should be able to plug in those numbers. Remember that when we talk about frequency, frequency is the opposite or inverse of time. And so instead of dividing by time, we're going to, or sorry, it's the inverse or opposite of period. So instead of dividing by period, we're now going to multiply by frequency because it's the opposite. So go ahead, you should be able to multiply those together and get an answer. If you want to check your answer, we're in the Q&A box. Don't put answers in the main chat. 30 seconds to work on that and raise your hands or send us a chat.
And period. And then we did the same thing using frequency, right? Remembering just that it's simple if you just think in terms of that the period and frequency are just inverses of each other. So we're really doing the same calculation, just in different forms. All right. But go and tell us how you feel about this. How are we doing? Use your color pointers and give us some feedback if you'd like. Yes, ma'am. So if there's nothing else, go ahead and submit your notes if you haven't already. If there are no questions, please feel free to log yourselves out. Have a great one, and we'll see you guys tomorrow. All right. Matthew, along with everyone else that probably missed a question or wanted to look back at one, you can stay behind for just a minute.